Okay, thank you. So first, I want to thank the organizers for allowing me to present my results here. So I'm going to talk about galaxy groups up to redshift 2.5, so not as far in redshift as the previous talks, using deep infrared surveys, talking about detection and quenched fraction of galaxies. It's a work done in collaboration with Sarron Conselice, and you will see the paper on the archive in a week or two, so stay tuned. Okay, so I'm first going to talk about the data we used, then talk about group detection with a new algorithm, DETECTIVZ, and then show some results on the quenched fraction in the groups and in the field using this data. So for the data, we use 3 of the deepest near-infrared surveys available, with a K-band selected photometric sample from Msun et al. In 2017. These are the UKIDSS UDS, Cosmos UltraVISTA, and Video CFHTLS D1 field, and we have between 10 and 30 photometric bands from UV to infrared in the different surveys. This reflects in the photometric redshift uncertainty shown here, here, here. You can see that we have different depth, and so this work is part of the REFINE project or REFINE surveys, which consists in reducing this data homogeneously to be able to combine these 3 fields and cover 3 square degrees in this redshift range. So the way we're going to work in terms of data products is we're going to use a probabilistic approach in this work. So we have photometric redshifts computed with EASY by Msun et al. In 2017. And in this work, we recomputed the physical parameters using SMPy, which is a SED fitting code. And and so this enables, by combining the two, to have 2-dimensional joint distribution for the physical parameters and redshift. So the idea is to take 1 dimension further, the classical that you probably know, so the PDF in redshift, and to have 2-dimensional probability distribution function for the different physical parameters. So here you can see in the realistic case for 1 galaxy, in the video survey, probability distribution function, of stellar mass and redshift, and here for specific star formation rate. And so the idea in this work is to use this information contained in this delocalized estimate of the parameters to account for correlated uncertainties between the different parameters in SED fitting and deal with the degeneracies when classifying galaxies. So we'll use a probabilistic framework. So let's move to group detection. So I developed for this work the DElaunay tessellation cluster identification with PhotoZ, the DETECTIVZ algorithm. So the main idea is pretty basic, as photometric redshifts have an uncertainty that is way larger than the size of a group or clusters in redshift space. We cut the galaxy catalog in redshift slices that are overlapping. We make 2-dimensional density maps in which we detect the peaks. As the slices are overlapping, the same true underlying structures is going to be detected in different adjacent slices. So we clean for multiple detection and obtain a final group and cluster catalog. So the specificity of DETECTIVZ is the way it uses this probability distribution function of stellar mass and redshift by doing a Monte Carlo sampling of this 2-dimensional probability distribution function to have 100 Monte Carlo realization of the galaxy catalog. And this is going to be used in density estimation. So for each of the Monte Carlo realization, we can compute a density map, and then we take the mean density map of a row realization. For each realization, the density map is made with DElaunay tessellation field estimation, weighted by stellar mass. So in the end, we have the mean DETECTIVZ here. And so it's similar to the Voronoi Monte Carlo algorithm by Cucciati et al. And Ng et al. But we add information about stellar mass in a probabilistic way. DETECTIVZ outputs a group catalog with a PDF of Z of redshift for the group, an estimate of radius, and for each group, member catalog with probability memberships. So now let's look at DETECTIVZ performances. To do this, we built mock data starting from Enriquez et al. 2015 light cones. We added empirically photometric noise to the redshift, stellar mass, and magnitudes and assign to each mock galaxy a PDF of M-star and redshift so that we can apply DETECTIVZ to the mocks. So as in the mocks, we know the true position and properties of the groups. We can compare it with our detection from DETECTIVZ. So here I show to quantify the selection function, the purity and completeness. So here as an example, I show for clusters at redshift less than 2, but we can look further down in mass and further in redshift. So basically, purity as a function of completeness, we reach 80% completeness and 90% purity, which is competitive with what is found in the literature. So we can also look at the properties of groups. They are well-centered, with 75% being miscentered by less than 0.35 R200. We have a low bias, low scatter redshift estimate, as can be seen here. So detective redshift as a function of true redshift. Pretty good estimation of R200. So slight bias overall, but low bias for the most massive halos, so for clusters. And we can build a competitive mass proxy, which is the total stellar mass, which is built by summing the individual stellar masses of member galaxies weighted by their probability memberships. So knowing this selection function, we can apply DETECTIVZ to the actual data, so the refined data, and build a 90% pure sample using the selection function. We are left with 448 candidate groups up to redshift 2.32. So you can see here histogram as a function of redshift and total stellar mass. And you can see as dashed, so overall detections, 90% pure sample solid line and field histogram are the newly detected. There are 186 of them, and we have 53 groups at redshift higher than 1.5. And so to study the quenched fraction, we're going to take a sample that is total stellar mass selected, so adding a cut here in total stellar mass. And so what I will show now is for 407 candidate groups at redshift 2.32. So let's move to the quenched fraction of the sample. So before showing you the results, I just want to give you a flavor of how we can use the delocalized estimate of parameters, physical parameters in redshift to study galaxy population in groups. So for example, for the classification between quenched and star forming, we used a cut in specific star formation rate. So at specific star formation rate being lower than 10 to the power minus 11 per year. But we do not use a strong cut. Instead, at each dead for each galaxy, we can compute a probability that the galaxy is quenched. So basically integrating in this direction the PDF of SSFR and redshift. And also it's pretty easy to get number counts as a function of stellar mass and redshift by just summing the individual PDFs, 2D PDF on these parameters. And as was done in Lopestan 1 in 2017, and we add one level of complexity here. As we know, the uncertainty on the group redshift encoded in this PDF of redshift that you can see in red here can marginalize out the redshift dimension, taking into account this PDF, and get an estimate of the number counts as a function of stellar mass for the group galaxies. So that's pretty nice. And so just the takeaway from this is that we built a new formalism that you will be able to find in the paper that uses this probability distribution functions. And this is good because it allows a better treatment of correlated uncertainties and degeneracies when classifying galaxies. So let's move to the quenched fraction. So I will show here the quenched fraction for galaxies with stellar mass between 10 to the 10.25 and 11 in groups, cores, so half R200, and compared to the field, so outside of the groups. So it's shown here for the field as dashed, and for the hierarchical model. So we build a hierarchical model with a linear redshift evolution. So you can see here. You can see that the linear model provides a good fit when comparing to binned quenched fraction, sorry, and that the group quenched fraction is higher than in the field up to redshift 2.3 if we take a 1 sigma confidence and a bit less at 2 sigma confidence. And so it increases with lower redshift, the difference between group and field. And we can compare to other works. So ZForge, Orels, Planck, and Go Green, we have a pretty good agreement and competitive constraints at redshift greater than 1, good agreement with ZForge and Orels. But we do find much lower quench fraction than Planck clusters and Go Green clusters. And so this could be indication that lower mass groups have lower quench fraction than massive clusters up to redshift 1.4. So in conclusion, what you can take out and what you can reuse from this is DETECTIVZ algorithm that is going to make public. It's a Python implementation. We will make public the group sample as well if you want to use it, and a new framework to study galaxy properties in groups. The main result is that the quench fraction is higher in groups than in the field at redshift less than 2. And to be able to interpret this in terms of a quenching mechanism that may happen in the groups, we will compute the galaxy mass function and radial distribution. And we will investigate also at some point whether the high redshift group that we find trace proto clusters or not. And that's it. Thank you.